AI music generators like Suno and Udio have moved from experimental demos to full production tools. But as these systems flood online platforms, a practical problem emerges. How do we actually detect AI-generated music in the wild? Most detection papers evaluate their models against a simple binary: original human-made tracks versus clean AI generations. That's a problem, because in reality, almost no upload is untouched. Songs get remixed, pitch-shifted, slowed down, re-encoded, or run through mastering plugins. These edits aren't AI-generated, but they introduce their own spectral and temporal artifacts. And here's the catch. Those artifacts can look surprisingly similar to the fingerprints left by generative audio pipelines. This creates what researchers call a hard-negative robustness problem. A recent study tackles this head-on by treating edited audio as the true negative class. Instead of comparing AI against pristine originals, they built a dataset of YouTube uploads grouped by reference song. For each original track, they collected AI-generated covers, human-edited versions, and the clean originals. The key methodological move here is reference song grouping for data splits. If you randomly shuffle clips, a model could just memorize melody, vocal timbre, or production style specific to one song. By forcing all variants of the same reference track into the same train, validation, or test partition, the researchers prevent data leakage and force the model to learn generation-specific cues rather than song-specific ones. The task is framed as a binary classifier, AI-generated versus edited. The model architecture is a pre-trained PaSST, which stands for Patchout Spectrogram Transformer. It operates directly on raw audio waveforms. Each video is decoded to mono, resampled to 32 kHz, and sliced into 10-second clips. Why 10 seconds? It's a sweet spot between capturing local generation artifacts and preserving enough musical context like timbre and short structural patterns. The PaSST frontend computes a log-Mel spectrogram internally. It uses 128 Mel bands, an FFT size of 1024, a window length of 800 samples, and a hop size of 320. At 32 kHz, that translates to a 10 millisecond temporal resolution. This log-Mel representation is fed into the transformer backbone. Training happens in two stages. First, the backbone is frozen while only the classification head learns, using a learning rate of 1 × 10⁻³. Then, the entire model is unfrozen for end-to-end fine-tuning, with a learning rate of 8 × 10⁻⁶. They use a weighted cross-entropy loss with label smoothing set to 0.03, slightly upweighting the edited class because it's the harder negative. Light augmentation like random gain variation up to 1.5 decibels and temporal rolling up to 1/10 of a second is applied to improve robustness. The results highlight exactly why this framing matters. At the clip level, the model achieves an F1 score of 0.836 on AI-generated audio, but drops to 0.720 on edited audio. That gap isn't a failure, it's the point. Edited audio contains compression traces, pitch shifts, and mastering artifacts that overlap with the spectrotemporal cues the detector uses for AI. At the video level, they aggregate clip probabilities using a fraction-based rule. If at least 33% of a video's 10-second clips exceed a confidence threshold of 0.6 for the AI class, the whole upload gets flagged. This video-level system reaches a balanced accuracy of 0.811, showing that while the task is tough, consistent generation artifacts do survive real-world editing. To understand what the model is actually doing, the researchers use Grad-CAM on the log-Mel spectrograms. Grad-CAM computes spatial importance weights by backpropagating gradients from the final class score into the activation maps of a deeper layer. When visualized, it shows exactly which time-frequency regions drive the decision. For correctly classified AI clips, the activation maps highlight localized harmonic bands and trenchant structures. For edited clips, the activations shift toward mid and upper Mel bins, where post-processing like equalization or compression leaves distinct energy distributions. The maps aren't cleanly separated into an AI zone and an edited zone. That overlap is exactly why the edited class remains a hard negative. The model isn't just looking at global loudness, it's tracking localized spectrotemporal deviations that both generative pipelines and human editing can produce. It's worth noting why a transformer-based approach was necessary. The researchers tested two baselines. A random forest classifier using handcrafted audio descriptors barely broke 0.52 accuracy, and F1, proving that global features miss the local spectrotemporal patterns needed here. A MobileNet V2 model trained on exported spectrogram images as images performed better, reaching around 0.74 accuracy at the video level, but still struggled with balanced metrics. Because MobileNet V2 is pre-trained on natural images, it doesn't natively understand audio structure or frequency resolution. PaSST, being pre-trained on audio set and specifically designed for spectrogram classification, captures the right inductive biases for this task. The study is transparent about its constraints. The edited class isn't a controlled set of isolated transformations. It's a messy collection of real-world uploads, meaning it's hard to isolate whether a specific edit caused a false positive. The dataset also leans toward vocal-heavy genres, leaving purely instrumental or classical music underrepresented. And while the PaSST baseline is strong, the paper doesn't compare against other modern audio representations like clap or audio MAE, leaving cross-model generalization as an open question. Future work needs controlled transformation benchmarks to measure exactly which edits, pitch shifting, time stretching, codec compression most frequently mimic AI fingerprints. The takeaway here is clear. Evaluating AI music detectors against clean originals sets an artificially low bar. In production, edited audio is the real world, and it acts as a persistent source of confusion. This research shows that while pre-trained spectrogram transformers can separate AI generation from human editing to a useful degree, the spectral overlap between generative artifacts and post-processing traces means we can't treat detection as a solved problem. Robustness testing must include hard negatives. If you're working on audio AI safety, content moderation, or generative model forensics, this framing should be part of your evaluation pipeline. Thanks for watching. If you want to dive into the paper or experiment with the PaSST implementation, I'll leave links in the description. Let me know in the comments how you think platforms should handle these edge cases.